This episode of Real Engineering is brought to you by Brilliant, a problem-solving website that teaches you to think like an engineer. One of the first things you learn in mechanical engineering is how to design your inventions in a way that is possible to manufacture and assemble. This is a skill that takes time to learn, primarily by working with machinists that look at your design and laugh at the incompetence of this young college kid. From placing fastener holes in inaccessible locations to placing sharp inner corners that no milling machine can achieve. So much of our engineering capabilities are dictated by what we can manufacture, and every time a new method of manufacturing is invented, it ushers in new technologies once deemed impossible. Just as the simple cylinder boring machine facilitated the Industrial Revolution, 3D printing may now be opening doors to new designs. Complicated hollow structures are now possible, allowing designers to integrate cooling ducts directly into parts, an incredibly useful tool for high-temperature parts like turbine blades and rocket nozzles. We can perform something called topology optimization, where we use finite element analysis, a type of stress simulation, to tell us exactly where material is needed, allowing us to generate the perfect structure for our application, similar to how hollow bones are formed, and thus allowing us to save on weight, helping lightweight vehicles to gain even more performance. Often, parts are machined down from giant blocks of raw material to their final form. In aviation, we measure this waste with the buy-to-fly ratio, which divides the weight of the final part by the weight of the raw material it was manufactured from. Imagine taking a material like titanium alloy, which can cost upwards of $30 per kilo, and then throwing away 90% of it in the manufacturing process. Needless to say, this is a massive source of increased costs that 3D printing could help reduce. All of these benefits can come together to unshackle engineers to form the perfectly shaped objects, and perhaps one of the most interesting applications of this is this incredible 3D printed Aerospike rocket engine that has incorporated liquid cooling channels directly into the rocket nozzle's interior and shaped everything optimally to provide a highly efficient rocket nozzle that can operate efficiently at many different altitudes. But even with all these amazing applications, we rarely see 3D printed parts outside of prototyping applications like this. It's clear that 3D printing can take human manufacturing to its next evolution, but what's holding it back? As usual, the first problem is cost. If we plot the price of a 3D printed part as a function of the number of parts created, it would look something like this. Its price will be dominated by initial machine costs, and that line will only marginally trend downwards as we print more parts, due to the insane time it takes to print a single part. After all, we are essentially welding hundreds of kilometers of metal powder together. To scale up our manufacturing, we need to buy additional machines, which will not lower our cost. This turns our traditional economies of scale on its head. Take an injection molded part. Early on, the cost will be dominated by the cost of creating an expensive mold needed to form the part. But once that is finalized, this machine can churn out piece after piece in rapid succession. We mostly just have to wait for the plastic to cool down before we can eject it from the mold and restart the process. This results in a graph that looks something like this, where our cost per part rapidly decreases as we build more, soon becoming dominated by the material costs. This means that it only makes economic sense to use 3D printing for parts that fall behind this break-even point, which is why it is used so frequently in rapid prototyping. If we can reduce the raw material cost with better supply and decrease 3D printer machine costs, we can lower this line and open up more parts to being replaced by 3D printing. That is gradually happening as the cost of these machines lower, in large part due to patents expiring in the last 5 years. However, it's not just cost preventing 3D printed parts from entering the market. This month I spoke with Professor Roger Reid, the founder of Oxmet, a company taking on the challenge of developing metal alloys and printing techniques to improve the material properties of these additive manufactured parts, to get a better idea of the material science that prevents 3D printed parts from being approved for even specialized small batch applications. We have thousands of years of experience, mostly through trial and error, of learning how manufacturing techniques affect the material properties of the metals we use, From learning how to tailor carbon content during iron ore smelting, to learning how each hammer blow can affect the crystalline structure of the metal. In particular, we've learned how the exact way we heat and cool metal affects its material properties as a result of its internal crystalline structure. But additive manufacturing throws away much of the techniques we've developed, forcing us to build much of our understanding up from scratch and develop completely novel techniques for studying and optimizing our material properties. One of the key areas of research in this regard is improving 3D printed metal fatigue life. Fatigue life is a measure of how many cycles of stress a part can sustain before breaking, because materials can fracture even below their ultimate strength if you cycle them at a lower stress for extended periods. This affects every metal and is the reason continual maintenance is always needed for machinery. We can visualize a material's fatigue strength by plotting on an SN curve, which places the magnitude of the alternating stress on the y-axis and the number of cycles it survived on the y-axis. For traditionally machined titanium, it looks something like this, whereas for 3D printed parts it looks more like this. Put simply, 3D printed parts fail much sooner, stopping many of the parts from being approved for applications they are best suited for, like aviation. So why does this happen? First, we need to understand what causes fatigue fractures. The primary cause of these fractures is crack growth, where small voids and imperfections within the part can force stress to divert and pile up in sharp corners and thus exceed the metal's strength locally and cause the crack to grow. The more imperfections present, the more likely your fatigue life is going to suffer. And 3D printed materials tend to have a lot of imperfections. We got a clearer look at why this happens when researchers used high-speed synchrotron X-ray imaging to get this phenomenal footage of the laser melting process, which revealed many of the phenomenon resulting in imperfections. Here, we have a powder bed of iron-nickel alloy called Invar 36, which has been turned into a powder by blasting a stream of molten metal with a high-pressure gas. This process is called atomization. As the laser moves across the powder bed, it melts it, essentially forming a weld line. You can see that this layer tended to dig into the powder bed, creating a track that varies in height. These sort of imperfections means the final product needs a surface machining to create a quality part. Although it's important to note that this study was specifically studying something called an overhang condition, where the part has no structure below it and has to build on the loose bed of powder instead. As the laser marches on, the powder in front of it gets blown away, meaning the laser no longer has metal powder to melt in that region and instead forms new beads of molten metal ahead of the original track, which eventually coalesces with the original. Finally, we see some worrisome behavior as the laser reaches the end of this track. As the molten metal begins to cool, we see pores begin to form in the upper surface of the track, the exact kind of imperfections that could allow crack growth to occur in the future. This study also varied several factors like laser speed and laser power to study their effects on the melt track's properties. Here, they increased the speed of the laser to a point where the metal particles did not have enough time to heat up and coalesce. In another experiment, they investigated the interaction of two melt tracks. Here you can see more pores forming as a result of overhangs trapping gas, and yet more pores form in the same manner as before as we reach the end of the track. Clearly, this process is much more complicated than just melting some metal powder together, and in the end, the final products that come directly out of a 3D printer are far from finished and need a significant amount of post-processing. For example, we can help close these pores by using a method called hot isostatic pressing, where we apply heat and very high isostatic pressure, which just means the pressure is the same in all directions. This maintains the overall part shape, but compresses and heats the part up enough to close those pores to improve our fatigue strength, but not enough to compete with traditionally machined parts. This, of course, pushes the cost bar higher, making 3D printing again less attractive for applications outside of rapid prototyping. And we have yet more material property issues to address. We explored the science of forging with my friend Alex Steele in a previous video. We learned how the internal crystal grain structure is one of the most influential factors in determining a material's final material properties, We can control the material's hardness and ductility by simply heating and cooling it in a particular way. Typically, when a piece of molten metal is cooled, crystals grow at random from individual nucleation sites and form crystal grains. The size and structure of these grains dictates so many of the metal's final material properties, and we've learned over thousands of years of metal forging how to get the best out of our materials. Once again, additive manufacturing throws much of this knowledge out the window, leaving us to start from scratch. We have learned that 3D printed materials tend to have these columnar grains that rise up in the direction of the print, and the grains tend to follow the direction of the laser, forming directional grain structures that can almost be thought of like the grains in a piece of wood. This means that how the laser moves has a massive effect on the material properties of the material, and thus we can use this to our advantage by tailoring our laser scan strategy. One of the most common laser scan strategies is the islands scan strategy, where a pattern like this is formed, creating 5mm islands of laser track paths oriented perpendicularly to each other. These islands are formed in a random sequence. This scan strategy, developed by Concept Laser, was created to alleviate residual stresses that form as a result of uneven heating and cooling within the metal, which can decrease the part's overall strength. Just another factor designers have to consider, and often requires the part to be placed in an oven after printing to help alleviate residual stresses. However, one study found that this scan strategy has some unique effects on the grain structure, creating those aforementioned vertical grain structures with fine grain boundaries between each island, and these fine grain boundaries had a high density of cracks, which again can grow and cause fatigue failure. There are, of course, alternative laser scan strategies like this helical one. Other researchers are attempting to use thermal and other specialized cameras inside the build chamber to observe the phenomenon like pore formation and inform the laser exactly how to operate with machine learning to maximize material properties. While I don't see this manufacturing technique ever being used for low-cost, high-volume parts where other manufacturing techniques are much better suited, if we can improve the fatigue life of these metals, we could start seeing them appear in more applications like that incredible 3D printed Aerospike engine we saw earlier. This is a very new area of research that could use more eyes. Just as I learned how to design to get the best out of carbon fiber composites and molded plastics over the course of my university life and industry experience, we are now seeing young engineers beginning their education with this form of design in mind, allowing them to create designs that were once deemed impossible. I believe there is going to be a fascinating meeting of material science and machine learning in the space to customize laser scanning patterns for particular parts and allow the machine to spot and fix defects as they happen. And I would imagine the overlap of material scientists and machine learning coders is a small pool of people at the moment. So perhaps this could be a career path for you, and you could start working towards it right now by taking this course on machine learning on Brilliant. This course will help you develop the mathematical skills needed to deeply understand how problems of classification and estimation work, and by the end of it, you will develop the techniques needed to take complex multivariable data sets and create machine learning algorithms to analyze them. Or you could complete one of Brilliant's daily challenges. Each day, Brilliant presents you with interesting scientific and mathematical problems to test your brain. Each daily challenge provides you with the context and framework that you need to tackle it, allowing you to learn the concepts by applying them. If you like the problem and want to learn more, there's a course quiz that explores the same concept in greater detail. If you are confused and need more guidance, there's a community of thousands of learners discussing the problems and writing solutions. Daily challenges are thought-provoking challenges that will lead you from curiosity to mastery, one day at a time. If I've inspired you and you want to educate yourself, then go to brilliant.org/real engineering and sign up for free. And the first 500 people that go to that link will get 20% off the annual premium subscription, so you can get full access to all their courses as well as the entire Daily Challenges archive. As always, thanks for watching, and thank you to all my Patreon supporters. If you'd like to see more from me, the links to my Instagram, Twitter, subreddit and Discord server are below.